Okay, so today is 9th of December. So inshallah, we will try to do as much as we can on chapter 8. Can you all hear me?
Yes, sir, we can hear you.
Okay, good. Okay, so let me just share the slides. Okay, so this is chapter 8. So we are in chapter 8. What we are going to talk about is memory, main memory. Okay, so we are going to understand what is main memory, and we are going to see how the operating system and the computer systems works in terms of handling memory management or main memory. First, you have to understand what are we going to look at in this chapter. Okay, point number 2, to discuss various memory management techniques, including paging and segmentation. All right. So what are these? What are paging and segmentation? Is basically in this chapter we are going to see how does operating system and the computer system handle memories, because you have to understand the operating system, the computer system runs multiple processes at one given point of time. So having said this, there can only be a few processes or few programs inside the memory. However, the memory has limited space. Inside the CPU, for example, the CPU can only run one process, and the CPU has limited space also. So there will be certain files only located inside the CPU, and certain files located inside the main memory or RAM, and certain files located inside the physical memory, or what we say as the uh, hard disk. Okay, so there are certain files divided. So if the CPU needs a specific file, it will first request from the main memory, which is the RAM, and if these files are not available inside the RAM, it will go and look at the hard disk. Okay, inside the hard disk. Okay, so basically, as you look at this in this diagram, this is how a simple memory management unit, memory management in a computer system works. You have the CPU, you have the cache memory, and you have the main memory. Okay, the cache memory and CPU are inside the CPU. Okay, so the cache memory is actually inside the CPU. So there will be certain files only stored inside the main memory, and also certain files which needs to be run will be stored inside the cache memory. So inside the CPU, there are, like you can see here, there are registers and cache memory only. Okay, so cache sits between the main memory and the CPU registers. Okay, but however, cache memory is actually inside the main memory itself. So in the hierarchy of memories, the smallest at the top is the registers, and then we have the cache memory, and then we have the main memory, and then we have the secondary memory, which is your hard disk. That is the hierarchy of the memory. Okay, so in order for the files to be loaded inside the inside the memory and the CPU, the operating system and the computer system works in such. This diagram here, over here, is the main memory, or we say the memory itself here. This one, the green one here. Inside the green one, the top of the at the top of the location will always be the operating system files. This is by default at any one point of time, right? And inside here, there are several process files. Okay, these process files are located in, is for the CPU to run. is for the CPU only. So if the CPU requests a specific file, let's say it requests for this particular file here, and look at this process file here, it will send a signal. It will send a signal to here, and there will be some calculations done in order to locate this specific file. Okay, to locate this specific file. Okay, so when it sends a request here, it will send an address. It will send an address. This address is to help the operating system to locate where is the file. Okay, where is the particular file? Okay, where is the particular file? So the operating system will send a file, an address for the computer system to change it and to locate that particular file, right? So the base and limit is where the particular file is. Okay, so the particular file would be between the base address and the limit address. Okay, so each file, each address which is sent by the CPU over here is checked between its base and its limit. The base is the starting address of a particular location, and the limit is the size of this particular location, right? So the CPU will send an address. So this address will be translated inside this system here, and it will be located where is that particular process file. This process file is inside the memory. Okay, so this base and limit registers is very important. Okay, and as you can see here, logical address. So what I mean here is the logical address is actually coming up from the CPU. Okay, because the CPU wants to locate one of these processes. So, but it doesn't know where is this process located. So it come up with a specific address. This specific address is known as the logical address. So the CPU comes up with a logical address. Always remember that. The CPU comes out with a logical address. Right? So where does this logical address, or how does it come up with? Okay. In order for the process to be processed, okay, listen to my words there. In order for the process to be processed, it goes through several stages. It goes through compile time, load time, and execution time. Okay, so execution time is the time when the process is being processed inside the CPU. That is the last stage. Yeah. Okay. So that is where you have your base and limit registers. The load and compile times are done before the process enters the CPU. Before it enters the CPU. This is quite logic to you because when you do programming, right? When you do programming, you will always compile your source code, right? When you compile your source code, it's actually doing compile time, and you will have a specific error sometimes. Okay, once it's okay, only then you can execute that command line. So similar to any process, before the process can be processed by the CPU, it goes through several stages, which is the compile time, load time, and last but not least, the execution time. Only the execution time is inside the CPU. Okay, only the execution time is inside the CPU. When the CPU needs a specific file from the main memory, it comes out with logical address, as I mentioned in the previous slide. Okay, so the concept of logical address that is bound to separate physical address space. So what is logical and physical address? So logical address is something generated by the CPU. As I showed you in the previous slides, when the CPU needs a specific file from the main memory, it comes out with something which is called a logical address. So logical address is generated by the CPU, right? However, this logical address is converted based on the base limit and the address limit. So it's converted, and it'll come up with a new address, which is known as the physical address. So where is this physical address located? This physical address is located inside the main memory. What is main memory? It's inside the RAM, right? So remember, logical address equals to CPU and physical address equals to RAM, or your memory. Logical address comes out with is generated by the CPU, and physical address is generated by the memory. All right. So if the once the CPU wants a specific file, it will come up with a logical address, and this logical address will be converted by the operating system into something which is known as the physical address. So the location of the physical address is the file that is needed by the CPU, right? So basically, it looks something like this, right? So this is the logical address. Okay, this is logical address, and this is the physical address as seen by the memory or main memory. All right, and as you can see from the previous slide, there is something which is called the base and limit. So the base and limit are registers located inside the MMU. What is MMU? MMU is the memory management unit. It's a type of hardware which calculates the location of the physical address. Where is the physical address? The physical address is inside the memory. Okay, where is the physical address? Is inside the memory. All right. So what is 14,000 here? 14,000 is what we say as the base register. Okay, base register. So as I explained in the previous slide, base register is the starting address. So logical address is 345 plus the base address. So you get 14346. So 14346 is the address of the particular location that is interested by the CPU. CPU does not know 14346 location. What it knows is the CPU needs to get the contents of address 346. So it signals out address 346, and this address 346 will be recalculated by the memory management unit together with the base register in order to get the physical address. Right. Sometimes the operating system also does swapping. Okay, swapping. Swapping means if there is no files which is required inside the main memory, then the files will be swapped out to the backing store and swapped in with a new process. Okay, swapped out. As you can see here, the diagram here does not involve CPU. CPU is not here. It is only between the main memory and the backing store. What is backing store? Backing store is like your hard disk. Sometimes the files that is needed by the CPU, it's not inside the main memory. So when that happens, the operating system will swap out file-file yang tak digunakan kat sini and put it back inside the backing store and swap in back new files which are required by the CPU. So this is what we say as the swapping process. Okay, the swapping process happens if the required files from the CPU are not inside the main memory. So when that happens, the operating system swap out the process which is not utilized by the CPU into the backing store, into your hard disk, and so re-swap in back files which are needed for the CPU. Right? So this is almost the same as well. All right. So in a contiguous allocation, all right. So now let's focus on the memory here. In a contiguous allocation, process files are stored side by side. Okay, the process files are stored side by side. So there are two partitions inside the main memory. One is the operating system files location, which is always located at the top. Okay. Why is it low memory? Because the address starts from the top to the bottom. So when the address is at the top, it's always at a smaller number. So 0, 1, 2, 3. So if we say this memory location, this memory size, the size of this memory is 100 megabytes, meaning the address starts from 0 to 99 here. So when we say the small, the low memory location, so it means it's at the top. Each process file is all contained at the high memory below here. So each process file is located inside the main memory here. However, there are certain files which are not located here, which is in the previous slide inside the backing store. So when it's inside the backing store or inside the hard disk, when there is a need to get those files, the operating system, they can swap out, okay, they can swap out any files from the main memory into the hard disk and re-swap back those files which are needed inside the main memory for the usage of the CPU. Okay, right. So basically, this is how it looks like. You have your CPU on the left-hand side. Okay, you have your limit register and your base register, and you have your memory here. All right. So base register contains the smallest value in the physical address, which is this one. And limit register contains a range of the address. That means the size of this. Okay, the size of this. The size of these limit registers are always the same. Okay, are always the same. If we are using contiguous allocation. Contiguous allocation means the size of the limit registers can be the same. Okay, so if you take this example, no, it's not the same here. Okay, that means the limit is always different. Sorry, the limit is always different. It can be different. Okay, and okay, it's between any files which is located, which is requested by the CPU, is between these two, which is between the base and limit. Okay, so let's say here the logical address requested by the CPU is 345. 345. Huh? So katakanlah, let's try to draw here. Let's say the requested logical address requested by the CPU is address 345, this one here. All right. First, okay, first it will check, the operating system will check if 345 is less than the limit address. So is 345 less than the limit address? Yes, it's way less. Next, it will just plus whatever base register, okay, plus base register, and you will get the answer for this. So base register is 30040 plus 345. So you will get the answer as 300 3885. Yeah, 3 5. So this is at address 300385 is the content of what is needed by the CPU. Okay, right. So in some other situations, there might be multiple partitions. Multiple partitions are situations where there are more than one process inside the main memory, and these partitions are not in the same size. They are different sizes. As you can see here, this is process 5, small, process 8 is big, and then process 8 disappears. What do you mean by disappear? Meaning to say it could be process 8 has been completed, or it could be there is no need to use process 8 at the moment, so it is swapped out, and a new process 9 comes in. So you have all these processes, and as you can see, the sizes are not the same. Okay, the sizes are not the same. All right. So in order for the process to be stored inside the memory, it goes through several different algorithms. It can go through the first fit, best fit and worst fit. Okay, what is the first fit? The first fit is an empty spot which is the biggest. Okay, or we can go through the best fit, which is the smallest, or we can go through worst fit, which is the biggest. Meaning to say, if there was more than one location, let's say there are two locations here. That means, let's say this is empty here and empty here. So ada dua ruang kosong kat sini. First one here and the second one here. Let's say there is a new process X coming in. So which location is process X going to take? Is it this one or is it this one? Let's say the size here is 10 and the size here is 15. And the process is 8 megabyte. So in first fit, that means this process can be located at the first location here because 8 is smaller than 10. That is the first fit technique. If you are using best fit, then the process will go through from top to bottom to locate the most available balance that is suitable. That means there is only very less balance. So you will go from top to bottom. This is 10, this is 15, and this maybe the center here is way too big. So it will take on the top only. This is the best fit. And the worst fit, this one here, worst fit, largest hole. That means it will go search from the top to the bottom, and it will take in this one here. Because let's say this one is 20 megabyte. So 8 will be fit inside here. Although this has a big balance, but it does not care. It will just take the biggest balance. So those are several algorithms that has been implemented. So these algorithms has been implemented during the early parts of computer system. However, now they only use best fit. There is no more worst fit and first fit anymore. Okay. So when you use these techniques, first fit, best fit, there are also the empty spaces which are not being utilized. So these empty spaces are known as the fragmentation. Okay. So in a situation whereby there is no, in situations like this, where let's say this is 10 and this is 15 space, 15 and ni 20. So 10 plus 15 is 25, 25 plus 20 is 45, right? 45. Okay. Let's say there is a new process coming in, process Y, and process Y needs to get 45 space. So this process cannot go in here because it's only 10. Y cannot go into this section because it's 20. It's still less than 45. And it cannot go in last year because it's 15, which is less than 45 as well. So these empty spots are known as the external fragmentation. Empty space which is outside the partitions. So if we were to rearrange these partitions, then you will get 45. So the operating system does something which is called compaction in order to rearrange this empty spot so that 45 can go in. Okay. Internal fragmentation, on the other hand, are fixed locations. Okay, fixed location inside the memory, and even though the files are small, but it gets one fixed location. So the unutilized balance is what we say as an internal fragmentation. Right? So compaction exists in examples like this. As you can see in these two examples, there are empty spots here and here and here. So when a compaction happens, all of these empty spots are reorganized and you get this one here. Compaction only happens to reduce external fragmentation. You can see here, external fragmentation. This is another example. So you have empty spots here, here, and here. So when you do compaction, when the operating system does compaction, it will reorganize these files and you have this spot at the bottom here. This compaction is similar to what you sometimes do in your PC. You do defragmentation. So this is almost the same as defragmentation. Why do you do defragmentation? Because you want to reorganize your file so there are no empty spots in between. If there are empty spots in between, sometimes it can slow down your computer, or sometimes it can just make your computer run very, very slow because there are empty spots in between those files. So when you clear up these empty spots and you reorganize them, you will actually, you will make your computer system more faster, and you are able to use those empty storage, those empty stores, papers. Okay, locations. All right, next let's go into segmentation. Okay, segmentation is almost similar to paging, only the program itself dibahagikan kepada beberapa segmen. Okay, so certain segments like you have here is the main program, square root, symbol table. So the program itself dibagi kepada several segments, and each segment will have its equal opportunity to be inside the CPU. So that's why we have the logical address here. So if the CPU needs a specific segment, it will request back from the memory management unit to bring in that specific segments. Okay, so these segments are kept inside the physical memory or the main memory. All right, so let's go back to paging. So how is paging done? So paging is between the logical memory, which is the CPU, and the physical memory, which is the physical memory, right? So each of these process are divided into several pages. Okay, several pages. Pages mean satu proses dibahagikan kepada a few pages. Okay, so if there is a requirement from the CPU to take in page number one, it will refer to this page table. Where is this page table? Page table ini inside the memory management unit. Memory management unit. Alright. So, bila dibaca sini, page 1 is inside 4. What is 4 mean? 4 means frame number. Frame number. So, where is this frame number? The frame number is all inside the physical memory. So, this is how you read the diagram here. So if the CPU needs information from page 3, page 3 is here. Look up at page table, or page 3's information is inside frame number 7, or frame number 7 is down here. Yeah. All right, that is how you look at it. And always remember, in paging, the size of this page, ini size ni, is the same as the frame size. Always remember that. Okay, the size of the logical memory is broken down into pages. Okay, and the frame pun physical pun dibagikan kepada beberapa segmen, which is called the frames. Okay, so the page size is always equal to the frame size. Always remember that. Okay, fix page size sama juga dengan frame size. All right, and then we have the offset value. Apa pula ni? What's that? Offset value generated by the CPU. Okay, so CPU will come up with, as we mentioned just now, logical address. Okay, so what is inside logical address? So logical address ada two information. One is the page number, central P, and another one is the offset address, PD. So when the CPU comes up with a logical address, logical address dalam tu ada dua information. One is what we say as the page number, another one we say as the offset address. So you always remember page number and offset address. So these informations will be checked on the page table MMU tadi to find out what is the physical address of what is that. Let's see, let me have an example here. Okay, never mind, we don't have. All right, so this is the CPU. It comes up with the page number and the logic offset address. Okay, this is it. So P dia akan check, mula-mula dia akan check dengan page table. Oh, it's inside frame number F. Okay, frame number F is here. Okay, cun. This is frame number F. Okay, it could be any frame lah. Kita tak tahu lah which frame. Alright. So the different. Okay, this is frame. So D ni is an offset address. So D's location, D D punya location is inside this frame. So somewhere along the line, that is what you're looking for. Okay. So this information dekat ruangan kat sini, this is what is needed by the CPU. Okay. Let us look again here. So the CPU comes up with two things, which is the page number, let's say page 3, and offset value. Offset. Or dalam example sebelum-sebelum ni, it uses D. Okay. So page number 3. Page number 3 is inside. Here is inside frame number 7. Okay, frame number 7. This is where it is. What is offset value D? Offset value D ialah dalam frame number 7 ni, which part of this frame number 7 ni besar? Which part of it is needed by the CPU? Is in this location. This particular location. So this particular location is what we say as the offset value. Okay. So this is another example. Okay. Sama juga. So this is page 0. This is frame 0. This is page 1. This is page 2. This is page 3. Why did I start with a 0? In any calculation, in computer calculation, you always have to start with 0. Okay, so this is frame 0, frame 1, 2, 3. Sorry, page 0, page 1, page 2, page 3. What is this? Frame 1, frame 0, 1, 2, 3, 4, 5, 6, 7. Okay, so let's take, for example, this one here. So this is in page 0. All right. Where is it? It's in frame number 5. Where is frame number 5? 0, 1, 2, 3, 4, 5. It's here. Let's take the last one here. This is page number 3. Frame 2. 0, 1, 2. This one. Nampaklah? MNOP, MNOP. Page 2. Frame 1. This one. Okay, that is how we look at it. Okay, now we have to do this question. Okay, so these are the formulas. Physical address equals to frame number plus frame size plus offset. Sorry, frame number multiplied by frame size plus offset. Page number of pages equals to program size divided by page size. Number of frames equals to memory size divided by frame size. Okay. All right. So get this in order first. Okay. Given a physical memory. So where is physical memory? Physical memory is your main memory lah. Okay. Size dia ialah 64 bytes. 64 bytes. So dalam kepala bayangkan 64 bytes. Okay. 64 bytes. All right. You got it. The page size. Alamak, page size. Where is the page size? Sebab page size ni is sebelah kiri tadi, yang dekat apa namanya CPU tadi. Okay. Page size is 8 bytes. So meaning each page ni ialah 8. Each ni ialah 8. So if this page size is 8, the frame size pun is the same, 8 as well. Okay. Remember, page size equals to frame size. Okay, so let's write this down. Page size equals to frame size. Okay, all right. So it says here memory size is 64 bytes. So kalau kita lukis, so this we are drawing the physical. So this is the physical. Okay. So page size dia 8. Formula kata page size sama dengan frame size. So, kalau frame size sama dengan page size, so how many frames do you have? So 64 divided by 8, you will have 64 divided by 8, berapa? 8. You will have 8 frames. So when you say you have 8 frames, since saya kata you start your frame size dengan kiraan kosong, that means you will start with 0 right up to 7. Okay, so you will have 8 but start with 0. So 0, 1, 2, 3, 4, 5, 6, 7. Okay, so this is 0, 1, 2, 3, 4, 5, 6, 7. Okay, right? So this is your physical, and this is your page table. This one. Okay, so now based on this information, you're supposed to do something. The physical address for logical address 23. So soalan tanya, what is the physical address of the logical address 23? Okay, let's see. So the question is asking, the logical address given is 2, 3. Okay, and you want to find out what is the physical address. Okay, so what is 2? 2 is the page number. Okay, and what is 3? Kalau you tengok from the previous slide, 3 is your offset value. Okay, so balik pada soalan ini, physical address equals to frame number that multiplied by frame size. Okay, plus offset. Okay, right. So 2 is the logical address 23. 2 ialah your page number. So page number ini ialah frame 3. Okay, write down frame 3. So dia kata frame number kan? Okay, write down frame number. Multiply by frame size. Multiply by frame size. What is frame size? Tengok formula ni. Page size equals to frame size. Okay. Page size ialah 8. So frame size also is 8. Plus offset value. What is your offset value? Soalan kata 3. So 24 plus 3 is 27. So 27 is your physical address given the logical address 2, 3. Okay. So how do you do this again? When you get a logical address, you are given 2 numbers. One is the page size, another one is the offset value. First, look at the page size. Where is it in the frame? So, page size 2 ialah frame number 3. Right? So that's one information. Next, you have your offset value, which is 3. Okay, you have that as well. So, what is your frame size? Sebab formula kata multiply by frame size. So check. Frame size, the formula says frame size equals to page size. Okay, we already know that. So 3, which is the frame number, multiply by frame size, which is also the page size, taruh 8, campur dengan offset value, which is 3, you get 27. That is your physical address. Okay, next one. 10. Okay, 10. So 10 is page 1, offset 0. Okay, simple. Page 1 is in frame number 4. Okay, multiply by 8. Plus dengan kosong lah. Sebab offset memang kosong. So you multiply, you get 8 times 3, 8 times 4 is 20, 8 times 4 is 32 plus 0, you get 32. Okay, okay, let's do the next one. Now, soalan kata, what is a logical address given the physical address 15 and 37? Now, in this question, it's a bit different. You are given the physical address. Sebelum ni, you are given the logical address. But in this question, you are given the, okay, you are given the physical address pula. Okay, you're given the physical address. Now, so what is the page size? Page size ialah, okay, page size is 8. Frame size pun sama juga. Frame size pun 8 juga. And you're also given the page number and the page frame number, page 0, 1, 2, 3, and the frame numbers are 1437. Okay, all right, so you're given all this. So now, can you calculate the logical address for 50? Siapa boleh calculate? I give you 2 minutes to calculate this. Okay, saya bagi you 2 minit untuk calculate ni. Okay, so you have to calculate the logical address given the physical address. Can anyone get it? Okay, Sophia, did you get it?
I couldn't figure it out, sir.
Anyone? Do you understand the question, Sophia?
I do, but then how do I know the offset and the...
Okay, tell me the formula. What's the formula like? What's the formula? How do we calculate? Just give me the formula first, and then we work backwards from there.
For the physical address equals to...
Okay, physical address equals to?
Frame number times frame size plus offset.
Okay, let's write that down first. So this is, what is it? Physical address 15, eh? Okay, let's go back here. Okay. All right, so we have, we are given, so this is our formula, right? Top one here. So physical address is 15, right? Down, physical address is 15. Physical address is 15. Okay. All right, done. So the formula says 15 equals to frame number. So we don't know what is the frame number. Multiply by frame size. Sophia, what's the frame size?
8.
8. Okay. Last step. Okay. Okay. This is what we know lah. Setakat ni, this is what we know. Okay. So we have physical address, soalan dah bagi. Frame number, we still have to find. And we have the physical frame size, sama dengan page size. We have that. And we don't know the offset value. Okay. Now, so now we have to find out what is our frame number. We do not know where is 15 inside this frame. So obviously we have to draw it back lah. So the draw it. So this is what I'm drawing here is your physical memory. Physical memory. So as I mentioned just now, the size of the physical memory is 64. And each frame size is 8. So you have to draw it from 0 to 7. So this is 0, 1, 2, 3, 4, 5, 6. So this is 0, frame 0, frame 1, frame 2, frame 3, frame 4, 5, 6, and 7. Okay. All right. So now, physical address 15. Where is physical address 15 kat sini? Is it in the first location? Is it in location 0? Or is it in location 1? Or is it in location 2? Where is it, Sophia? If each of these kotak ni size dia 8, 8, 8, 8, 8, 8, 8, where is it? Please somebody answer.
In 1.
1.
1. Good. It's in 1. In location number 1. So frame number 1. So frame number 1 is inside page number
0.
Bingo. So this is 15. So 15 is inside dalam ni lah. Kenapa you kata 15 dalam ni? So this is 8. One kotak here is 8. So the next one is 16. And then the next one is 24. Next one is 32. So 15 is inside location frame 1. So frame 1 is inside here. So frame 1 is inside page number 0. Okay, so we have frame number 1 here. Multiply by 8 and plus offset. Okay, all right. So you get lah, you get one here. All right, chun. Okay, frame number 1 is page number 0. Okay, chun. Okay, so this is our formula. Formula we have done. We have got the page frame number. Okay, chun. We have got 1 here. We are multiplying by our frame size, which is also the page size, and we don't know the offset, so plus offset. But we know 15 here. Okay, 15. So upon doing everything, you dah tukar-tukar semua. Offset equals to what is offset? Sama dengan 7. Pandai. 7. Okay, chun. So now we have our offset number. Clap. Yay, we have that. Now, how do you write the answer for logical address? As you remember just now, logical address has 2 components. It has the page number and it has the offset value. Okay. So now we have the offset value. What is the page number?
0.
0. So the answer is logical address equals to 0, 7. Sama dengan physical address. Tadi soalan apa? 15 kan? 15. A15. Alright. So logical address 0, 1 equals to physical address 15. Are you with me?
Yes, sir.
Okay.
Okay. Alright, let's do the next question. Logical address, oh ni 37 ni jangan buat dulu. Okay, do the next one down there. Question number 3. Page number and offset value for each logical address 13 and 18. Okay, so they want you to do the same thing. Okay, so you can do the same thing, or you can find out what is the physical address for question number 3 wants the page number and offset saja, which is the logical lah, for each logical address 13. Okay, sorry, this is a wrong question, sorry. Okay, please disregard question number 3 ya. Soalan silap. Okay, do the last one. Find out what is the logical address for physical 37. Find out what is the logical address for physical 15. No, physical address 15. Physical address 37.
Logical address dia 45.
45. 45 ke?
Yes, sir.
Okay, sekejap saya pun nak katik sekarang. Okay, betul. Alright. Okay. 45 ke 15? I got the 5 right? The offset tu betul. Sophia or somebody else? What do you get?
I got 15.
15. Tahu tak kenapa silap tadi? Siapa yang jawab 45 tadi tu?
Saya.
4 tu kenapa? You understand why you are wrong? Because you answer kat sini. 4 tu, frame number. You kena bagi page number.
Oh, okay.
Itu je, beza je. Okay? Saya baru nak bagi bonus mark tapi you dah salah jawab, so tak jadilah. Okay, good. Alright. Okay, so I think we have done for today. Yang lain-lain tu is just examples you can read lah. There's nothing much. Okay? Okay. So I hope all of you understand about calculating the paging examples today. You can check out these recordings nantilah. Okay? So for you to understand more. Any questions so far?
All good, sir.
All good, eh? Okay, thank you. Inshallah, I'll see you in the next class. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you, sir.
Thank you, sir.
Thank you, sir.